why you would want to make small sizes of materials for better energy conversion towards sustainable energy. So if you look at kind of this nice vision of a sustainable energy future, and I know over the past week you've been hearing about different components of this, you might imagine that you could use things like photovoltaics, which you just heard about, to collect sunlight and put it directly into electricity. You may want to store that sometimes as a battery or a supercapacitor. Other times you might want to use the sunlight to directly make a fuel. This is called photoelectrochemistry. You could take the fuel, maybe it's hydrogen, you can store it, and when you want to use it, you might react it in a fuel cell to get efficient conversion back into electricity. So what I'm going to assert is that those devices shown there and many others actually have the same phenomena underlying how they work. Basically, they're the same physical and chemical phenomena that are common to photovoltaics, fuel cells, supercapacitors, batteries, and so on, in the following way. So each process basically creates positive and negative charge carrier. In a photovoltaic, it's an electron and a hole. Sometimes it's an ion and an electron. It moves the charge, and then it recombines the charge. And let me just give you a couple of examples. This is a photovoltaic, which you just heard about. Basically, it takes sunlight, converts it into electrical energy. The way that works is light is absorbed. It creates these charge carriers, positive and negative charge carriers, electrons and holes. They're separated. In this case, they're separated by having two different types of semiconductors next to each other, and then they're recombined and current flows in a circuit. But you can draw a very similar picture for something like a fuel cell. And I know you heard about fuel cells earlier in the week. Fuel cells basically they do something very different. They take chemical energy and convert it into electrical energy. But again, what you're doing is you're generating charged species here at these interfaces. You have, in this case, one of your charged species is a positively charged ion, and the other one is electron. You move them around this system, you recombine them, and you get conversion of chemical energy into electrical energy. So how can we improve this process? And what I want to explain to you is that there are ideas out there that if you make things smaller, you can actually improve a number of the steps in those processes which are common to these different devices. So the first thing, these are just some examples, but if you make things smaller, charges don't have to move as far. I mean, that's kind of the obvious. So for example, I showed you in the photovoltaic, we had these two types of semiconductors. If you put them, if they're closer, then this carrier doesn't have to move as far. That might help get it collected more efficiently. You might also be able to absorb more sunlight if you make things small, and there are different ways this could happen. One idea is that you might be able to tune the band gap, which basically is referring to the absorption spectrum of a material through a process called quantum confinement. And a completely different idea is that if you're talking about separating and recombining charge at an interface, you can often get more active sites for reactions, and these are referred to as catalysts, in a very small scale system. So you can access different surface sites than you would have if you had the bulk material. So these are some of the ideas that you might be able to get those processes to occur more efficiently, the generation of charge, the motion of charge, and the recombination of charge if you made things small. So if we go back to this picture of a sustainable energy future, here are our big devices, the photovoltaics, the photoelectrochemical reactor, and what I'm showing here are lots of small things all around it. So the idea is if we make nanostructures or nanomaterials an inherent part of these different devices, we might be able to get more efficient energy conversion. And I should point out that many of these already have nanostructures and nanomaterials, and what we are looking at is how can you make that better, make things smaller, and put them in the right places to get better energy conversion. So this idea is actually the foundation of the center that I'm co-directing with Professor Fritz Prinz on nanostructuring for efficient energy conversion. So it's funded by the Department of Energy. It's about, it's a $20 million grant over 5 years. And I'll show you who's involved in it in a moment. But the idea is to take these general concepts of how nanostructuring can enhance efficiency of energy conversion and look at them at a very fundamental level and see if we can really improve energy conversion in photovoltaics or fuel cells and other devices. Okay, so we have a team here at Stanford as well as some partners outside of Stanford. I'm showing you the faces because you're either new to Stanford or you're here, so you can seek out all of the different participants. These are the participating faculty. We have about 10, crosses a number of different departments, and we have partners as well who are actively involved, all working in this idea of nanostructuring for efficient energy conversion. So what that means is we have to make the materials, we have to characterize them, and we have to start to put them into different model systems to see if they actually improve things. So these are just some pictures of some of the nanomaterials that were made in the center, which we call SNEAK, Center on Nanostructuring for Efficient Energy Conversion. That's the acronym. For a lot of different applications, some of these were being looked at for catalysis, some for photovoltaics, but the idea is we have different strategies for how to make things really small. So I'm going to give you a few examples to show you how this might be put into effect. So we'll start with charges not having to move as far. So there's an idea that's been explored for several years on what I'd call nanostructured architectures for photovoltaics. And this really is just trying to take advantage of the fact that if you have the two different semiconductor materials near each other, so they don't have to, charge carriers don't have to move very far, you might be able to collect more of them and have a higher efficiency. But you also want to be able to collect a lot of the light. So to do that, you have to have a lot of the material there. So this design allows you to do both things. So if the sun is up here, you can have a lot of a path for the sunlight to come through, but if you generate one of these positive or negative charge carriers, they only have to go to the side and can be collected very quickly. So there's a lot of interest in different ways of making this. There are different types of solar cells that would take advantage of this structure. A lot of the organic solar cells effectively do already. The type you heard about in the previous talk, and this is a dye-sensitized solar cell where it has all these sort of nanoscale material interfaces separated by something that's much thicker in this dimension. Or you could do it out of things like silicon, which is shown here. This is work out of Caltech. So one of the things we're doing here at Stanford, and a number of groups are working on this, is different strategies for making these materials. How do you make these nanostructured materials with that kind of interdigitated morphology that I showed you? I'm not going to talk about the experimental work. I'm just going to tell you we also are modeling this. This is work done by one of my graduate students, Art Wang-Peralong, where we're really trying to see, do you actually benefit by having this geometry? You can collect the charge carriers better, but maybe there are other losses. And in fact, there are other losses with a structure like this. And through the modeling, an analytical model, you can actually explore subtle differences between this type of structure and that type of structure, and it turns out they're pretty significant. And through models like this, we can try to understand what would be the best nanostructured geometry to get the highest energy conversion efficiency for a particular kind of device. This was modeled for cadmium telluride. If you do it in high-quality cadmium telluride, you actually are worse off if you do this kind of structure. But if you start to get low-quality cadmium telluride, and that's the kind you want to use this structure for because you want to be able to get back some of the charge collection, but be able to do it in low-cost materials or low-cost processing. It turns out that you do have a big advantage in efficiency with this kind of structure. Okay, so let me give you another example. I'm worried about that gong. I heard the gong earlier, and I definitely don't want to hear it with me. More light may be absorbed. So how do we do that? There are actually lots of strategies for doing this, but let me just give you this one example of tuning the band gap through quantum confinement. And one way to do that is through a very small semiconductor particle called a quantum dot. So quantum dots, as it says here, are basically small particles on the order of a few nanometers in size. And one of the biggest benefits is that you can tune the band gap, which is basically the energy of light that's absorbed by this particle, by changing its size. So bigger particles absorb more in the red, smaller particles absorb more in the blue, and this is through a quantum mechanical phenomenon called quantum confinement. And here's an example from the literature of different colors of different quantum dots. Same material, just changing by size. They're stable, and there's some other phenomena that people have reported that make them also attractive. But the main point here is, just as an absorber for something like a photovoltaic, we can tune the band gap just by taking the same material and making it of different sizes. And this is an example from our group on taking cadmium sulfide, which is a semiconductor. We're growing the quantum dots by a technique that I'll explain in a minute. So at this point, that doesn't really matter. But these are basically glass slides that are covered with a whole bunch of these particles. And what we're doing here as we go this way is we're changing the size. We're increasing the size. So over here, it's absorbing more in the blue or ultraviolet, so you don't really see much color. And as it shifts more to the red, you see the color very clearly changing. And this is what you need when you're trying to tune something to absorb as much of the solar spectrum as possible. Okay, so the last example is this area of catalysis and separating and recombining charge if you make things small. So here, the example I want to show is one that's a little more complex than just a catalyst. This is a system for splitting water to produce hydrogen for fuel, and you also get oxygen. So the idea is you need something called a photoelectrocatalyst to do that. It's something that absorbs the sunlight and can carry out this chemistry at its surface. And what you're seeing here is you would have two electrodes. One would do the oxidation, and one does the reduction. And one of them generates oxygen, the other one generates hydrogen, and you'd want to separate those, but you take your hydrogen as your fuel source. But it turns out that a material that does this is really hard to come by. Okay, so it has to do the following. It has to be a good absorber of sunlight. So typically that's a semiconductor, absorbs sunlight well. That's kind of where it ends for a photovoltaic. But here you need to do more. You need to actually catalyze some chemistry at its surface. And so something that may absorb sunlight well doesn't necessarily do that well. And also you're dunking it in this very reactive water where it's oxidizing and reducing. And a lot of semiconductors will just fall apart very quickly in that set of conditions. So you need to come up with some material that's stable. And people have been looking for decades for a kind of material that does this well. And they have some that do things okay, but don't do all three of those things well. So one of the projects within the center, SNEAK, is to look at material like this, the photoanode, and decouple those two requirements in a structure like this. Okay, so the idea is this is a multi-layered structure. First of all, you'll notice it's nanostructured. Okay? The reason for that, one reason, is that this part, the center part, is going to be doing the absorbing, and I've just told you that you can maybe tune the absorption spectrum by changing the size of things when they get really small. So here we might be able to tune the absorption of that semiconductor by changing, say, the diameter of these rods here. And we also get a lot of surface area because to generate the reaction, it only takes place at the surface, so you need that. But what we're going to do here differently is we're then going to coat it with a very thin layer of something which is chosen not because it absorbs light well, but because it is a good catalyst and is stable. So we're taking these three requirements and separating them into two materials, and conceivably you could have three materials. You could have something coating it for stability and another, say, nanoparticles on it for the catalysis part. So a number of different materials are being looked at. This is actually a collaboration between 4 different groups here at Stanford. My group, Tom Jaramillo in chemical engineering, Bruce Clemens in material science, and Xiaolin Zheng in mechanical engineering. So you see it takes a lot of different skill sets and different disciplines to come together and make some of these nanostructured devices. So what I'm going to tell you about just briefly is, have I gotten the 5 minutes? I didn't hear the gong.
80 seconds.
Oh, okay, good. I have just enough time. Is how are you going to make something that coats this with this great material that's going to be stable and catalytically active, but it has to be extremely thin. The whole system is going to be in the nanometer scale in this dimension. And if it gets too thick, you can't get the electrons and holes through it efficiently. So my group, and actually several groups here at Stanford, use a technique called atomic layer deposition, which is a vapor phase technique for depositing materials. And I'm just going to go quickly through this. You pulse these different reactants through. Again, they're coming in the vapor phase. So the first reactant comes, and it reacts at the surface, and you sort of flush out what you don't want. And then you come in with another reactant, and you purge that out. And if you repeat this over and over again, you can actually grow up a film of all kinds of different materials, including the kinds of things you might want to coat for a photoelectrocatalyst. So this is just some examples of results, not of the photocatalyst, but this is titanium dioxide grown by this technique of atomic layer deposition on a germanium wafer. Here's a silicon nanowire that's been coated all around it by platinum. And this is actually one of the strengths of this technique, because you can take some very complex nanostructured material and you can coat it uniformly all around, and not many techniques will do that. So this is just the last slide. This is the material we've been looking at, manganese oxide, as a catalyst. You can deposit it by this atomic layer deposition. and just showing that it actually works quite well as an oxygen evolution catalyst. It even works as the opposite, which is an oxygen reduction catalyst. So this is one of the reactions you need to split water into hydrogen and oxygen. And it does pretty well compared to some of the real standards that are known to be the best catalysts for this reaction. Oh, and the thing I forgot to mention is why choose this material? It's because it's pretty abundant. It's not one of these expensive precious metals. So if you can get a good catalyst out of something that's inexpensive, you actually have a more realistic chance of making a lot of these devices cheaply. Okay, I just want to end by showing my research group. Some of the stuff involves the people that I described in the center, but the work that I told you about from my group, Art, I mentioned, Steve Herron, you're going to hear from Pendar and Katie, and then these are the rest of the participants, and this is the name of the center. We have some information on the center. It involves about 30 grad students and postdocs here at Stanford. You can go to the website and find out more. Okay, great.
So we have time for questions. Oh, questions.
When we're looking at cost, what are the proportions of cost of materials versus cost of processes like atomic layer deposition?
I mean, it depends very much on the exact process. So one of the criticisms of that technique, which I guess you've honed in on, is that that looks expensive, right? Atomic layer deposition, you need vacuum pumps, and you have to pulse things through. And one of its strengths is that you can deposit materials at sort of 1 angstrom at a time. But that's the weakness, because it would take a long time to deposit material, and time is cost. So there are two arguments to that. One is for prototyping, it's perfectly fine to use techniques like that. But I will say that people and companies are looking at making high throughput ALD reactors, and they're actually applying them now to some solar cell applications, which sort of by definition have to be low cost, silicon solar cells. So the processing cost, you want it to be low. You want both to be low, the materials cost and the processing. And in this case, it's probably a little bit on the high end, but the price is coming down pretty rapidly as more engineering is done into these types of reactors.